Hello and welcome to another episode of Physical Attraction, the TEOTWAWKI specials. In this one, I'll be talking about the end of everything. What's going to happen if we manage to survive the 21st century and the 22nd, get over all of our problems? What will happen to the planet? What will happen to Earth? We sort of touched on this in the last episode, Utopia, where we talked about how perhaps a super advanced human species might be able to deal with the sun naturally getting warmer over the next billion years, and they might in fact be able to cancel that out. But of course, eventually one imagines that the evolution of the cosmos, of galaxies, of stars and planets, will overtake even our species' ability to do anything about it. So if we manage to survive the sun gradually heating up, there might be a bigger problem before the sun runs out of hydrogen. See, Monty Python and the Galaxy song have it right. Our galaxy is only one of millions and billions in this amazing and expanding universe. Physics is stunning, and the reason is that it exists on so many different scales. On impossibly small length scales, we have no idea what's going on. Things are strange and weird and quantum mechanic-y. Then we move up towards the scales of subatomic particles, then the world of atoms and molecules, the world of microscopy, the world of us, macroscopic objects and the objects we know, the world of mountains, the world of worlds, the world of stars and solar systems, the world of galaxies and stellar systems, and maybe the world of universes too. And you can talk about length scales that vary by orders and orders of magnitude, from the Planck length of 10 to the minus 20 all the way up to huge length scales that go across the entire universe. And the world of galaxies is going to be the next thing that has an impact on us after the star, because our galaxy is heading towards the Andromeda galaxy at a rate of knots. And in around 4 billion years, we're going to collide with it. If there are any observers left on Earth, they will be treated to quite the sight as the Andromeda galaxy will loom large in the sky, vast and real cryptic above us. But this intergalactic car crash isn't going to be explosive, at least not in the way you might be expecting. Imagine it, soundless in outer space, billions of stars sliding towards each other at phenomenal speeds, a gravitational dance on a scale larger than you can possibly imagine. But because most of galaxies are empty space, there will be few, if any, star-on-star collisions. And this is obvious when you think about it. Just think about how little space our sun takes up in our solar system as a whole. The chances of our star being hit by another interloper, or even another star passing remotely close to this solar system, are very unlikely. The two galaxies will first pass completely through each other like ghosts, and then fall back together again under their own mutual gravitational pull. The net effect of all of this will cause an incredible thing to occur. As the two galaxies pass through each other, dance around each other, and fall into one another, they will merge. The supermassive black holes at the heart of the Milky Way and Andromeda galaxies will merge together, irresistibly drawn to each other. Two hearts become one, and, pulling in matter towards the new supermassive black hole, the inner region will become very hot and heavy. A burst of stellar formation, literally called a starburst, will likely follow in the inner regions, and the galaxies will merge together, forming a new, elliptical galaxy. They've already nicknamed it Milkomeda or Milkdromeda, our new home. Although it may not be our new home. Our current best simulations of the cosmos predict that there's a big chance that the net effect of all of this gravitational ballet would be to shove the sun and the solar system further towards the outer edge of the galaxy, and there's perhaps a 13% chance that we'll be ejected from the galaxy altogether. Our solar system may even end up going on a wild ride that involves sinking towards the super-duper massive black hole at the centre of the new galaxy, before being slingshotted around it and exiting the merged galaxy altogether. But even if that did happen, it wouldn't make a huge difference to conditions on Earth. It sounds strange to say this, but you have to remember just how far apart stars are in the solar system. For scale, if everything is shrunk so that the sun is the size of a ping-pong ball, then the nearest star is a pea 680 miles away. That's why any collision is so tremendously unlikely, and why it doesn't really matter that much if we stay in the galaxy or not. The influence of these stars on our solar system as a whole will be important. But locally, the planets will continue orbiting the sun, and the temperature and light on them is probably going to be pretty similar. For them to be anything other than pretty similar, you'd need the stars to become reasonably close to the planet, and that just seems unlikely. So even though our solar system as a whole might be rejected from the new merged galaxy, like a poor unwanted soul left to wander lonely across the whole universe, we'd still be alright. For a little while. After 5 billion years, the Sun will run out of hydrogen fuel and start predominantly burning helium. And this, which we found out in the hot and heavy episodes right at the start of this show, means that the Sun will expand until its radius is way larger than it is today, probably all the way out to the orbit of Mars. And then anyone left on Earth is going to have a problem, because not only would we be much closer to the surface of the Sun, but it seems that our planet will be sucked into the Sun and roasted to a crisp. This wasn't always considered to be a slam dunk as to what must happen. Scientists briefly thought that the Earth might survive. The reason for this is that as the Sun goes through its life cycle and expands, it's losing mass all the time. This makes sense, of course, because the solar wind is constantly driving a stream of particles away from the Sun. Plus, remember Einstein, E=mc²? Mass is just energy in another form. So the fusion reactions, which release energy, mean that the Sun is losing mass all the time. And over a timescale of 5 billion years, that will be a significant amount. The gravitational pull of the Sun on the Earth will be less, and will drift out to a wider orbit as the Sun loses gravitational influence. So is this enough to save us? Well, it turns out no, it's not quite. We will be at a wider orbit when the Sun runs out of hydrogen and expands to 250 times its current size and swallows up Mars. But we won't be far enough away to avoid the red planet's fate. Instead, there'll be a tidal effect of the Earth's gravity on the Sun. Essentially, this means that the Earth pulling on the Sun will deform the surface of the Sun, causing it to bulge outwards. The Sun and the Moon pulling on the oceans, which causes them to bulge outwards slightly at different times, is what causes the tides. That's why it's a tidal effect. It's when gravity has different magnitudes across the length of an object, due to the object's finite size. So this outwards bulge of the Sun that's going to be caused by the Earth is going to lag slightly behind the Earth's orbit, because the Sun's material will take time to respond to the pull. As a result, it's pulling us backwards slightly. Imagine the Earth orbiting the Sun, and then chasing the Earth on its orbit is a bulge in stellar material. That bulge in stellar material, caused by the Earth, will pull us backwards slightly, always towards it. And this means that the angular momentum of the Earth's orbit gets transferred to the Sun. And that's really, really bad. Because angular momentum in orbital mechanics is what sets your distance from the thing that you're orbiting. The more angular momentum you have, the further out you can be. With less angular momentum, though, as we're being dragged back by the lump of Sun, we'll drift towards the Sun, and even our wider orbit won't be enough to save us. The first sign that things are going wrong will be that as the Moon drifts towards the Earth, it will pass inside the Earth's Roche lobe, which means that mass transfer between the Earth and the Moon can start. In practice, this means that the Moon will start to split apart and fragment, with debris from the Moon pounding the surface of the Earth, like a series of meteorite strikes, as the Earth itself spirals down towards the Sun. And that's just the start of our problems. As it spirals in, the Earth will be engulfed, swallowed into the Sun that gives us all our life and all of our power, and that's that. But since we've already talked about magical, scientific, technological utopias, let's go completely insane. Humanity is looking very smug indeed. Let's say we found a way to move the entire Earth on its orbit, possibly through everyone jumping in unison, or putting every politician on one side of the Earth and allowing the massive expulsion of hot air to propel us away from the Sun. This might actually help us earlier on when we're trying to deal with the increasing heat and luminosity from the Sun. We could gradually drift the Earth outwards in its orbit to keep liquid water on its surface, even if it means going out towards the orbit of Neptune. And finally, with our politician-fueled ramjet drive, we're in the habitable zone for the Sun as a new red giant. Home and dried. Well, for a little while. As we talked about in the stellar evolution episodes at the start, every phase of fuel burning for the Sun results in contraction or expansion, and every phase lasts for less and less time. Jetting the Earth backwards and forwards so that it's always in the stable orbit is going to get increasingly difficult as the Sun goes through more and more phases of its stellar evolution. And towards the end, these phases of stellar evolution only last for a few hours, so it will be very difficult to keep up with that. But let's say that the new version of that supercomputer, the Oracle from the last episode, is up to it. Oracle 11. Providing we're not dealing with Oracle Vista, in which case we're all screwed. After all, we're desperately clinging to the Earth now, our home. We've been through so much together, billions of years of history. A little thing like the sun we orbit around isn't going to wreck everything. And the sun won't die with a bang, but with a whimper, sort of. It's not big enough to undergo a supernova, as we said in the stellar formation episode. Instead, it's going to cool down and gradually eject all of its outer layers in a planetary nebula. I repeat my advice from many, many months ago. Please Google image search planetary nebula. You won't be disappointed. The degenerate core of the sun is going to be left behind as a white dwarf star, around the size of the Earth, but incredibly bright. With the outer layers lost, the sun will lose a lot of its mass, and naturally the orbit of the Earth would drift out to be about twice as far from the sun as it is at the moment. But since humanity has seized control of that orbit a long time ago, this doesn't really matter in our fantasy, does it? Is there a habitable zone around a white dwarf star then? Could we imagine that if we could somehow survive the sun's dying convulsions we could move back in? Well, yes, maybe, sort of, probably. I mean, as you can probably imagine, I'm ignoring all kinds of complications here in this fantasy scenario where we fanatically want to stay on the Earth. The white dwarf's surface, you see, is much hotter, and so the peak of its radiation is going to be at a much higher wavelength. The Earth will be bathed in dangerous ultraviolet light. But that's not going to matter, because surely in 5 billion years we'll have invented an effective kind of sunscreen for that kind of thing. We have actually seen planets orbiting around white dwarf stars. In a lot of ways, because the white dwarfs are so small and bright, it's actually easier to detect this kind of planet. You see, our usual method of observation is transit observations. That is to say, you look at a star, and you see how its brightness changes when a planet passes between us and the star. That's tricky when the star is massive and the planet is tiny, but it's much easier with a white dwarf which is around the same size as the planet. Then you can have a decent fraction of its light blocked out periodically as the planet orbits around it. But the issue is that because of how these white dwarfs form, these little planets have almost certainly been through the wars. If they haven't been scorched to a cinder by falling into the star, then they're probably on very weird elliptical orbits that cause massive temperature changes that are inconsistent with what we know about life. But if life somehow survives the transition of the sun into a white dwarf, we can delay our fate on our happy little motorised Earth for a little while longer. White dwarf stars, as we mentioned in those star episodes, are really just stellar remnants. No nuclear fusion is taking place in the white dwarf, so there are no sources of new energy for the star, but it continues to shine, cooling down. And this means that it's cooling down all the time. Now, the cooling process takes a very, very long time. So long that we don't think there's been enough time for many of the white dwarfs that currently exist to fully cool down yet. It takes billions of years for a white dwarf to cool. In this intervening time, it's considered quite likely that passing stars will drag planets out of their orbits. One will eventually come close enough, and the Earth will probably drift away from the sun anyway. Even if we manage to avoid this, it doesn't look good. Eventually, the sun will radiate away all of its energy. It will become a brown dwarf. Eventually, it will no longer be warm enough to sustain any kind of temperature. All liquid water will freeze, and the Earth will become a hunk of rock, barely warmer than the background universe, like so many other dead planets. And then, surely, it will finally be the end of life on Earth. What, you really thought I was going to give up this easily? 1 quadrillion years into the future now, and we haven't managed to invent some kind of sun-independent planetary central heating? Dedicated listeners will remember in the Malthusian catastrophe episode, I talked about how continually increased use of energy is unsustainable because eventually waste heat literally boils the planet away. But if there's no sunlight, that kind of effect could be useful. And maybe, as long as we can battle against entropy and disorder for long enough, we could pull in more matter, harness the power of the stars that still burn, and keep us alive. You know, there are even people who've done calculations about extracting energy from rotating black holes, because that's a process that goes on for many, many billions of years, even after perhaps some of the stars have gone out. Okay, let's imagine that we managed to shake our dependence on the sun. I mean, if you believe Ray Kurzweil in our episode on the singularity, it's meaningless to try to predict what our technology is going to look like even 50 years from now. And futurists talk about ours as a Type 0 civilization, because we haven't harnessed the power of our sun yet. A type 1, 2 and 3 civilization can harness the power of more and more stars. So if these goals are attainable by flawed humanity, probably by this time we won't depend on the sun at all. So maybe my assumptions about what kind of technology the human race is going to have in a quadrillion years are, a little bit dodgy. And at any rate, it's probably going to be a good idea to colonise other planets, just in case. And if we manage this and spread far and wide enough, then it seems like our fate is going to be tied, not to the ultimate fate of the planet Earth, but to the ultimate fate of the universe. One of the really amazing things about physics is that we can say such staggering things. And what have we got to go on? We have logic, we have experiments on Earth, and we have starlight. Now the starlight comes in many forms, and we can design a lot of really ingenious experiments, and we can assume that the laws of physics are the same everywhere, and these kind of things do get us a really long way. But the fact that in the last few thousand years we've gone from basically knowing very little to actually being able to make what we think are quite decent predictions about the ultimate fate of the universe and everything in it, that's wild, and don't let anyone tell you otherwise. So what do we think is going to happen? Well, I'm going to do a full series of episodes about cosmology soon, because it's super important to explain what dark matter is and what dark energy is and what my beloved cosmic microwave background radiation is, and partly just because this stuff is so utterly amazing and wonderful. So I don't steal the thunder of those episodes, I won't do too much explaining of why, but instead I'll explain what might happen. The predominant theory, the main one that we have evidence for, although this is very disputed, is that the universe is going to go on expanding forever and ever. And the second law of thermodynamics is not helpful to us in a universe that goes on expanding forever. It states that entropy, disorder, will always increase. And while it's not straightforward to apply a definition of entropy to the whole universe, or to treat the whole universe as a classically thermodynamic system, what it looks like will happen is something like the following. Gradually, processes occur that tend to transform energy into heat energy, or radiation. And as the universe expands, the wavelength of that radiation is stretched. It cools down, and it spreads out across an ever-expanding universe. A finite amount of energy in an infinite universe is a recipe for disaster. If the universe itself lasts long enough, it's going to approach the final steady state, the final equilibrium, where energy is pretty much evenly distributed, which means that the temperature will be effectively zero everywhere, or so close to zero that it doesn't matter. When this happens and entropy is maximised, things are maximally disordered. It's not just a case of things being too cold for humans, who require the world to be at a relatively roasty 300 Kelvin to be happy to live. The thing that entropy is that the more entropy there is, the less free energy there is to be harnessed, the less energy can be converted into useful work. In a universe where the second law does the only thing the second law knows how to do, there'll be no free energy to be harnessed at all. And all of our theories indicate that free energy is needed for any kind of information processing at all. Without the ability to process information and harness energy, no kind of life, even simulated life, could possibly carry on. The stars that exist will stop shining, and around the same time actually, the formation of new stars will drop to zero, because the gas clouds that used to form them will be too sparse and spread out across the vast universe to collapse into new stars. Soon enough, no stars will shine. Even black holes, those monstrous creatures, will slowly evaporate until they no longer exist. All shall fade. All shall fall quiet. And everything will be gone forever. To quote Global Catastrophic Risks, the cheerily titled book that I've used as a resource for lots of these shows, quote, "At the end of its life as an ordinary star, the Sun is scheduled to become a white dwarf. In the long run, the Sun will end up as a small block of hydrogen ice. As it faces its demise, our galaxy will gradually evaporate, scattering its stellar bodies far and wide. The effective temperature of a stellar system is given by the energies of its stellar orbits. In the long term, those energies will fade to zero, and the galaxy will end its life in a cold state. For the universe as a whole, the future is equally bleak. The universe will expand forever, and the cosmos is likely to grow ever colder and face an icy death. The universe began with elementary particles and radiation because the background was too hot for larger structures to exist. In the future, it will also end up as elementary particles and radiation because the cosmos will be too cold for larger structures to remain intact. From this grand perspective, the galaxies, the stars and planets that populate the universe today, are but transient phenomena, destined to fade into the shifting sands of time. Stellar remnants, including the seemingly resilient black holes, are also scheduled to decay. Even particles as fundamental as the protons may not last forever. Ashes to ashes, dust to dust, particles to particles. Such is the ultimate fate of the universe. No life can survive the heat death of the universe. All that will be left is a cold soup of long wavelength photons, electrons, positrons, and neutrinos. That is all there will ever be, for infinite time. And eventually, even the billions of years of chaos and stars and fun and life and excitement will seem just like a blink of an eye to this eternal nothingness. I guess with that depressing but maybe somewhat comforting note, I'll leave off on the one thought that I always seem to drift to when I think about physics on this vast, cosmological, cosmic scale. As I type this, I'm sat underground in a flat in London. It's night time, and I can hear the roar of the tube train passing through on the underground beneath me, carrying humans towards their destination. Their hearts are pumping blood around their bodies, and their neurons are firing, letting them think, learn, and feel, for another day at least. I can hear the thrum of cars as they Doppler towards me and Doppler away again. I can hear the drunk people in the pub across the road yelling at each other and laughing. I can step outside, into the back garden, the cool night air, and squint through the light pollution to see the moon and the stars. I can even hear seagulls in the distance. If this really is the universe, if this really is how it ends, and our best evidence suggests this to be true, then we are lucky indeed to live during this utterly ridiculous part of the universe's history, while the candle still burns, while there is still light and life and things to see, in the split second before the infinite nothing. And I think that, in the end, Jeff Mangum got it right. How strange it is to be anything at all. Thanks for listening. We'll be back with some regular episodes soon. Until then, you can visit the website www.physicspodcast.com. You can tell all of your friends about the show. Stay safe and be well.
You better make some preparations. There's no time for hesitations. Compile a list of tips.
Our theme music is Get Ready for the Apocalypse by Astrometrics.
To get ready.